Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
1,3-butadiene, C4H6, is a colorless, highly flammable gas used mainly as a building block monomer for synthetic rubber, latexes, and plastics such as SBR, polybutadiene rubber, NBR, neoprene, ABS, and SB latex. Large-scale butadiene production became strategically important during World War II because synthetic rubber became essential for tires, vehicles, aircraft, and war materials. Industrially, most butadiene is recovered from the crude C4 stream produced in steam crackers. Heavy feeds such as naphtha generally produce more C4S than light feeds. Steam cracking operates roughly around 700 to 900 degrees Celsius, and butadiene separation needs extractive distillation because C4 components have close boiling points and can form azeotropes. Modern extraction technologies commonly use selective solvents such as NMP, DMF, acetonitrile, furfural, or dimethylacetamide. BASF/Luma-style NMP extraction is widely used for high-purity butadiene recovery. Safety is critical. 1,3-butadiene boils at about 24 degrees Fahrenheit, minus 4.4 degrees Celsius, has an LEL around 2%, and OSHA's exposure limits are 1 ppm 8-hour TWA and 5 ppm short-term exposure limit. Every moving vehicle, every industrial belt, every oil-resistant gasket, and many plastics around us depend on one small molecule, 1,3-butadiene. It is not a famous chemical like ammonia or methanol, but without it, the modern tire industry, automotive rubber parts, ABS plastics, and many industrial elastomers would look completely different. Before synthetic rubber became common, industries depended heavily on natural rubber. But during World War II, rubber supply became a strategic crisis. Chemical engineers had to create a reliable artificial rubber supply. Butadiene became one of the key building blocks for this revolution, especially in styrene butadiene rubber used for tires. Butadiene is a conjugated diene. That means it has two double bonds separated by one single bond. This structure makes it highly reactive in polymerization. In simple words, butadiene molecules can link together like chain links, forming elastic materials, rubbers that can stretch, recover, absorb shock, and resist wear. Butadiene is not usually used directly by consumers. It is converted into polymers and chemical intermediates. Its biggest use is in synthetic rubber, especially tires. Styrene butadiene rubber gives abrasion resistance, polybutadiene improves resilience, and nitrile rubber provides oil resistance. In most modern plants, butadiene is not made as the main product. It is mainly recovered as a valuable co-product from steam cracking, the same process that produces ethylene and propylene. When naphtha or heavier hydrocarbon feed is cracked at high temperature, a mixed C4 stream is formed, and hidden inside that stream is butadiene. In most modern plants, butadiene is not made as the main product. It is mainly recovered as a valuable co-product from steam cracking, the same process that produces ethylene and propylene. When naphtha or heavier hydrocarbon feed is cracked at high temperature, a mixed C4 stream is formed, and hidden inside that stream is butadiene. Steam cracking is a thermal process. Hydrocarbon feed is mixed with steam and passed through furnace coils at very high temperature. Large hydrocarbon molecules break into smaller unsaturated molecules. Ethylene is the main target, but depending on the feed, the plant also produces propylene, pyrolysis gasoline, hydrogen, methane, and a valuable C4 fraction. The crude C4 stream is not pure butadiene. It is a difficult mixture of hydrocarbons with almost similar molecular sizes and close boiling points. Ordinary distillation alone cannot easily separate them. This is where chemical engineering becomes interesting. If two chemicals boil at nearly the same temperature, a normal distillation column struggles to separate them. Butadiene and other C4 hydrocarbons behave like this. So engineers use extractive distillation, where a solvent is added to change how the components behave inside the column. In extractive distillation, a selective solvent such as NMP is introduced into the column. The solvent has stronger affinity for butadiene and more unsaturated C4 components. Butanes and butenes move overhead as raffinate, while butadiene is carried downward with the solvent. A good solvent must be selective, stable, low-corrosive, recoverable, and economical. NMP, N-methylpyrrolidone, is widely used because it can selectively extract butadiene from mixed C4 streams and can be regenerated and recycled back to the process. A butadiene extraction unit is built around a solvent loop. The crude C4 feed enters the main extractive distillation column. Raffinate leaves from the top. Butadiene-rich solvent goes to a stripper, where butadiene is removed. The lean solvent is cooled and recycled back to the column. The overhead stream from the first extraction section is called raffinate 1. It still contains useful C4 chemicals like isobutene, butenes, and butanes. In a petrochemical complex, nothing is wasted. Raffinate 1 can become feed for MTBE, alkylation, butene 1 recovery, or other downstream units. Crude butadiene may contain traces of acetylenic compounds, such as vinyl acetylene. These are dangerous because they can increase instability and polymerization risk. They must be removed or controlled before final product storage and shipment. After extraction and stripping, the butadiene stream is purified further. Light gases and heavy impurities are removed. The final product must be clean enough for polymerization because even small impurities can affect catalyst performance, rubber quality, color, odor, and product stability. At normal temperature, butadiene is a gas, but it is commonly stored and transported as a liquefied compressed gas. Inhibitors such as TBC are added to reduce polymerization and peroxide formation. Storage systems need pressure control, relief valves, gas detection, grounding, fire protection, and emergency flare connections. When butadiene demand is high and steam cracker supply is not enough, companies may use on-purpose routes. One route is dehydrogenation of N-butane. Hydrogen is removed from butane in catalytic reactors at high temperature. This route can produce butadiene directly, but it requires careful heat management, catalyst regeneration, and separation. Another route is oxidative dehydrogenation, or ODH, of butenes. In this process, oxygen removes hydrogen as water. Because water formation releases heat, ODH can be more energy efficient than simple dehydrogenation. But the challenge is selectivity. Engineers must avoid burning valuable hydrocarbon into carbon monoxide and carbon dioxide. A future-looking route is biobutadiene from ethanol. Ethanol can be made from biomass, and then converted over catalysts into butadiene. This is not yet the dominant industrial route, but it is important for low-carbon rubber and sustainable tire production. Butadiene requires strict safety control. It is extremely flammable, heavier than air, and can form explosive mixtures. It is also classified as a carcinogenic workplace hazard. That means plants must use closed systems, leak detection, ventilation, exposure monitoring, flame-proof equipment, proper grounding, emergency shutdown systems, and trained operators. The plant runs like a carefully balanced machine. If solvent flow is too low, butadiene slips into raffinate. If reboiler heat is wrong, separation suffers. If temperature rises too much, polymerization risk increases. Operators continuously monitor pressure, temperature, flow, composition, and alarms. This is the full story in one diagram. Butadiene begins as a small fraction inside a complex cracked gas mixture. Through extraction, solvent regeneration, impurity removal, and final purification, it becomes a high-value polymer-grade monomer ready for rubber and plastics manufacturing. Butadiene production is a perfect example of chemical engineering value creation. A small component hidden inside a cracked C4 stream is separated, purified, stabilized, and transformed into materials that move the world. Tires, belts, seals, gloves, plastics, and industrial rubber all begin with the engineering of one simple but powerful molecule, 1,3-butadiene.